easy part. Now let's do first. If this is all that we're going to do, we probably wouldn't have gained that much compared to what we already have. In fact, I don't think I've ever seen this type of induction used for propositional rule sets. For first order rule sets, it's probably at least as widely used as the FOIL style, or probably more widely used. But it's definitely widely used there. So how do we take this propositional idea and go to first order? Okay, that's the last thing we're going to look at today. So, first of all, let's see how we do first order resolution. Right? We saw how to do resolution in the propositional case. The difference is that now in first order we have predicates and arguments, not just Boolean symbols. Okay? So how do we do resolution in this case? This is actually where things get more interesting. This, for example, what gives Prolog the power of a full programming language is that it can do these argument combinations and replacements and come up with answers to non-trivial questions. So the big difference, as we saw, between propositional and first order is that now we have arguments, right? And the difficulty or the interesting twist that arguments introduce, right, is that now finding a literal and its negation, in order to do resolution, is no longer just a matter of having something like, R and not R. Now we have something more like, human of Socrates. And on the other hand, we have something like, a human of X implies mortal of X. Right? By the way, I omitted the universal quantifier here because that's what people do in Prolog, right? But this just means that, all humans are mortal. Okay? Now notice, what is it that you want to happen here in order for your inference to go through, right? What I would like to do is to infer from this that M of S. Right? But the problem is that this rule here doesn't even talk about S, right? It talks about X. So how do I make the connection? Well, the connection comes from the fact that this rule applies for every human, right? Every X. So in particular, it applies to Socrates, it applies to S. So what I need to do in order for this to go through is I need to unify H of S with H of X. This is the technical term unify. What we're doing here is called unification. I want to make these guys be the same. Why do I want to make them be the same? Because remember, H of X implies M of X is the same thing as not H of X or M of X. Once I've turned these two guys into the same thing, now they resolve. One is the negation of the other. So what do I need to do in order to unify them? Well, in one of them I have S. And in the other one I have X. So what I need to unify them is to replace X by S. This is called substitution. What I literally do is I substitute X by S. In general, I might need to substitute a whole bunch of things, so I'm going to have a set of these things. This is called a substitution, right? In the simplest cases, what it does is it replaces variables by constants, like the variable X by the constant Socrates, so that universal rules can apply to concrete people or to specific instances of people, right? This is really where deduction does its thing, okay? So I do the substitution in order to have two littles that unify. And then once they unify, boom, I can apply a resolution just as in the propositional case, okay? The power of this rule, of course, is that it's saying something in one short expression for all 7 million people, right? In propositional logic, if I wanted to say that people are mortal, I would have had to say this for every single person separately. Anna is human, therefore she's mortal. Bob is human, therefore he's mortal. This is ridiculous. In first order logic, instead of 7 billion statements, I just make one. Okay? But then I need my substitution in order for the variable to actually apply to the constant. Okay? Everybody follow this? Very good. So, what does first order resolution mean? I no longer have to just look for two littles that unify, that one is the negation of the other. I have to look for two littles that I can somehow unify by finding the right substitution. Like, for example, in this case, replacing X by S did the trick. Okay? And I'm going to represent that set of substitutions by theta. And L1 theta is L1 with that substitution applied to it. So L1 theta, for example, is L1 with every occurrence of x replaced by s. Okay? So for example, this h of x implies m of x. After applying that substitution, will become h of s implies m of s. Okay? And then at that point, right, if I have found that, if I have found two literals such that with some substitution one becomes the negation of the other, at this point I can apply the resolution rule to those literals subject to those substitutions. So that is going to go through only when x is Socrates. It obviously will not go through when x is Aristotle. Okay? Unless I also happen to have Aristotle in my database, but let's ignore that case. Okay? And then once I have that, everything works as before. So, a slightly glib thing to say would be, well, resolution in first order is just the same as in propositional logic, except with substitutions. Okay? So what is my rule now? Is that I form the resolvent by including all the literals from C1 with the substitution theta, and all the literals from C2 with the substitution theta, except for L1 with the substitution theta, and not L2 with the substitution theta. Notice that apart from the phrase with the substitution theta that I just repeated 4 times, this is exactly the same sentence as before. Okay? So, here's my recipe, right? What is my resolvent going to be? It's C1 minus L1 with the substitution theta union C2 minus L2 with the substitution theta. Okay? And again, this formula is the same as before, except with this new interesting little theta added. Okay? Questions? All right, so finally, right, we're scaling the mountain and we're almost at the summit. Here comes the summit, right? The base of the mountain is wide, but the summit is thin, and indeed, this summit is very thin. It's just this one little point. Okay? So, what am I saying here? Right now you have the pieces. All you have to do is put them together. You know how to do propositional inverse resolution, right? You know how to do first order resolution, and now we just have to figure out how to do first order inverse resolution. So what's going to happen? Remember, I'm looking for C2, right, given C and C1, right? So what's going to appear in C2? What literals must C2 contain? Think back to the propositional case again. It's going to be very similar, right? It has to contain, right, what is this whole part here doing? Right, let's start by just revisiting the propositional case, and let's pretend that the thetas aren't even here. Okay? I have C minus C1 minus L1, right? This is what we had before. It's all the littles in C that didn't come from C1 have to come from C2. You agree? Very good, but now comes this interesting part. So by the way, I forgot to say, theta 1 is the substitution that I applied to C1, and theta 2 is the substitution that I applied to C2. Right? This is a new complication. Right? I'm looking for C2, but there's also some substitution. Finally, when I have C2, when I apply it to get my resolution, right, it's C2 with some resolution, with some substitution. Right? So let's call that theta 2. Right? So can anybody tell me what this theta 1, theta 2 to the minus 1 is doing here? Theta to the minus 1, of course, means the inverse substitution, right? So first of all, what is theta 1 doing here?
The normal substitution that you applied to.
Exactly, right? This is what I applied to C1 to get C2, right? So that goes through in both cases, right? Whether I'm doing, deduction or induction, right? So I took all these things in C1, right, and I put them through theta 1 to get to C, right? And now it's comparing to that I'm going to see what needs to come from C2, right? Very good. Everybody got this, or anybody has questions? And now comes the most interesting part. What is theta 2 to the minus 1 doing there? This is where you really see that this is an inverse operation that we're doing here, right? I have some stuff that appears in the final clause that came from C2, right? But by deduction, I applied theta 2 to C2 to get to C, right? So if I want to get from C to C2, obviously I have to apply the inverse substitutions. If I substituted, x by Socrates to get here, right? Now to go the opposite way, I have to replace Socrates by x, right? And notice, this is not some little detail. This is where the induction happens. Induction happens when I go from something that was about Socrates to something that's about any x, any human. Okay? So this theta 2 to the minus 1 here is absolutely crucial. We're going to see an example of this shortly, our same, study, no material example. Okay? All right, so can anybody tell me what the second part is here? What is this not L1 here?
It's the hook that's going to hook to C1.
Right, this is the negation of the literal that disappears from clause C1, right? Just as before. Just as in the propositional case, right? Everybody agree? And now what is theta 1, theta 2 to the minus 1? Well, it's the same thing that happened on the other side, right? L1 got theta 1 applied to it to get to C, but not to get to C2. I need to apply the opposite of theta 2. And then I get my C2. Okay? Everybody agree with this at this very abstract level? Of course, I recommend that you go over this a little bit more carefully, in your copious free time. Also, Mitchell has a very good, explanation of this, so, I encourage you to look at that. But in the meantime, just to make things clear and concrete, let's look at an actual example. And this is by, one system that does this is called Seigel. So let's look at an example of what Seigel would do here, right? So here's our family example. So actually, I lied. This is not the no material example. It's a much more interesting one. This is our original, father-child example. And what we're going to try to do here is actually something more ambitious. We're going to try to learn the concept of grandchild. This example is going to allow us to actually show the full process, or something more like the full process as opposed to just one step, right? What we've been seeing so far is really only one step of resolution and for only one step of inverse resolution. But a lot of the power of this comes from when you can go through a whole proof tree and have all these inverse steps, right? Basically what's going to happen in a real system like Seigel is that I have this proof that I would like to make, right? I want to prove this result. And now I'm trying to form the proof tree, but there's holes in it. There's things that I need to have to make the proof go through, and those are the things that I'm going to induce. Okay? So what we have here is a very simple proof tree, and we're going to see how we fill in the holes. So let's start, on the left side here, right? So here are some of the facts in my knowledge base. Okay? So this is my data. Some of the facts in my database. I know that Father Tom Bob. Okay? This is a fact. And I know that Father Shannon Tom. Okay? And I also know that grandchild Bob Shannon. Okay? And presumably I have a whole bunch of examples like this, but let's just focus on one here, right? What I want to do is infer from this the concept of grandchild. Okay? And let's just focus on the father case. There's also the mother case, but let's just focus on father to keep things simple, right? What is the rule there, right? Let us preview what needs to happen here. What is the rule for somebody being somebody's grandchild as a function of father? A is B's grandchild if what? If A is C's child and C is B's child, right? Right? So if it is the case, Shannon is a grandchild of Bob, right? Why is that the case? Because Bob is the father of Tom, and then Tom is the father of Shannon, right? Everybody agree? We know this. The question now is how does the machine learning system figure it out? Well, let's see. Let's apply, our first order inverse resolution ideas, right? So this is my C1 and this is my C, right? So if this is my C1 and this is my C, what do we need to have in C2? Well, first of all, what has shown up in C that was not in C1? Grandchild, right? Right? Grandchild appears in C and did not appear in C1. So it must have come from C2. Everybody agree? Right? So here's grandchild. And let us not worry about the arguments just yet. Right? So what is the other thing that has happened from C1 to C, right? Grandchild appeared, but something disappeared. What was it that disappeared? Father, right? So what do we know about C2? What does it have to contain? Right? It needs to contain not father. You agree? Okay, very good. So here's the clause, right? Grandchild or not father. Right? But now let's look at, but this is only half the story, right? And maybe not even the most interesting half of the story. Let us look at the arguments. Well, so first of all, let us look at people, right? Who appeared and disappeared between C1 and C, right? Well, let's see. Bob appears in grandchild, right? Bob appears in C, but Bob did not appear in C1. So where must Bob have come from? It must have come from C2, right? And Bob appears as the first argument of grandchild, right? So it must have been the first argument of grandchild in C2. There are no two ways about that. Okay, everybody agree? Very good. Well, likewise, Tom has disappeared from C1, right? So we need something in C2 that negated that. We need something that negated father with Tom as the second argument. Well, here it is, father with Tom as the second argument. Okay? Right? Now what remains? What remains is the most important part. What remains is Shannon and X. Right? Why couldn't I just let this clause here be grandchild Bob Shannon? Would that work? Right? So this literal, right, grandchild Bob Shannon appeared in C, right? So it must have come from C2, right? Well, if in C2 I just put grandchild Bob Shannon, does that do the job?
You haven't really gone anywhere, you just moved the problem up a level.
No, well, let us not worry about induction for just a second, right? The problem that we're trying to solve here is like, I need the literal grandchild Bob Shannon to be in clause C2 so that it appears in clause C, right? And let's say that I just put that literal in clause C2, right? That works, right? So there's nothing wrong with clause C2 being grandchild Bob Shannon or not father, Shannon Tom, right? Because remember, X is the same on both sides, right? So why did I do this? Why is my theta 2 replacing, or my theta 2 to the minus 1 actually be Shannon replaced by X? Why did I do that? I didn't have to. Why did I do that? At the same time, I'm free to do that, right? Because with this as the substitution, if I have grandchild Bob X, and then I replace X by Shannon, I get grandchild Bob Shannon, and everything goes through, right? So this also works. But why did I go to the trouble of replacing Shannon by X?
Because grandchild Bob Shannon proving grandchild Bob Shannon is not really interesting.
Precisely. I'm trying to induce general knowledge here. I'm really not interested in just understanding, who in this family is whose parent. I want to know the general rule for what makes somebody somebody's grandchild. Therefore, I want to go from specific people to statements about all people. And that's why I deliberately replaced Shannon by X. This is what's giving me generalization. Okay? Remember, inversion often has a lot of options. We're seeing a place where we have many options, and so what we do is we pick the option that we like best. Not all inductions are equally good. I want to do more here than just make this go through. I want to learn the most general and accurate knowledge that I can. Okay? Any questions? You can certify yourselves that this all works by, just now taking this as an ordinary problem of deduction and saying, if I have this C1 and this C2, do I get C? And, clearly you do, right? But, you can go through this as an exercise at home. Okay? So far, so good? Okay, but now there's one more step, right? But now basically you got the hang of it, right? It's just with a more complicated clause, right? So now let's see. Now we're going to go to this part of the proof tree, right? And now what happens? Well, grandchild appears here, right? And it does not appear here, therefore it must have come from here, right? Very good. And again, look at this thing, right? I had here grandchild Bob X, but now I have grandchild YX because I replaced, Bob by Y, because again, I'm trying to generalize, Okay? And now notice that actually the literal father does appear here and here, but now I have to look at the arguments and the substitutions very clearly and see, look, what I have here is Father Tom Bob, and what I have here is not Father X Tom. There is no way to unify these two, right? Why do I have two fathers here, right? Why couldn't I just use the father from this side? Well, notice that the father here has Bob as the second argument, and this father has Tom. There's no way to unify these two. This one is talking about Bob being the father of Tom, and this one is talking about Tom being the father of someone. There's no way to equate them. Okay? So again, what has to happen is that this one has disappeared, right? So I need to have its negation over there to make it disappear. And this one here, right, has to have appeared, so I need it here. At this point, things are getting pretty complicated, and again, I suggest that you go through this, at home. But hopefully, the general idea should be clear. I have put into this clause all the stuff that is in this one, but couldn't have come from here, and the stuff in this clause that disappeared, I negated it and put it in here. Plus, I took all my constants and generalized them to variables because I want the general. And lo and behold, I have induced the definition of grandchild, right? Again, if you turn this into implication form, it says that if father xz and father zy, then grandchild yz, yx. Bingo. Victory. Okay? And of course, the beauty of computers is that they will do this thing for you millions of times in seconds without complaining. So, we have this tiny little proof tree here just to understand the concepts, but, then you run Seigel and it chugs for, a day, and it spits out all these great rules about, what makes a molecule carcinogenic. Good deal. Now, truth in advertising, it's not that simple. More things have to happen, but at a high level, this is what's going on. Okay? Questions? Okay, very good. It's late. We're almost done. Let me just mention one little thing. Progol. When you apply these systems like Segal in practice, you get a huge combinatorial explosion because there's all these ways of taking literals and combining them and of finding resolutions and whatnot. So you need something else to control the search. And one very popular thing, and this is what Progol does, is that it first tries to find actually kind of the opposite of what I just showed you here. It tries to find a specific rule. Not the most general possible rule, but a specific one that accounts for the data. And then it does the search based on that rule, only within what that rule permits. Okay? And this is the usual trade-off of overfitting, right? In some ways, we're less powerful. We might, have fewer things that we induce now. On the other hand, I really, really have helped to control my search. And now it's much more efficient, and I'm much less likely to overfit. Okay? Again, I'm not going to go into the details of that here, but it's important to realize that doing this in practice is not just applying something like Seigol out of the box. There's things like Progol and systems like Aleph and whatnot. There's a lot of stuff in this area by now. Okay? All right. Any questions about any of this? Thank you for your persistence and alertness. The good news is this was the hardest lecture in the whole class. We will see other things that are hard in other ways, but in some ways this was the hardest. And also, we've seen how to take rules to the first order level. You can take anything that we're going to see in the following weeks to first order level. We're not going to talk about how we do that here because there's no time for everything. But at least now you have a sense of how machine learning can be powerful enough to induce, programs from data, not just, a simple, spam classifier based on words and whatnot. Okay. So remember, we have no class next Wednesday because I'm traveling. And what we're going to have is, you must be gluttons for punishment, and we are certainly gluttons for meeting our punishment. We're going to record in next week's class here tomorrow. So, probably most of you can't come, and that's fine. What that means is that you can just, watch the class anytime that you want on your own time, including, next Thursday at 6:30 p.m. Or you can come to the class here or remotely if you want. Okay? And after that, the class is going to be on the web, right?
It's still at 6:30 tomorrow.
No, sorry, I forgot to say. Tomorrow it's at 4. So I sent an email to the list about this. Did everybody get it? Yeah. So unfortunately, we couldn't do it at 6:30 because the room was not available.
Did you get to put the 2 math quizzes?
No, this went to the course list. So If you have not subscribed to the course list, please do, because we send these announcements there. And anyway, so assuming you missed that message, just to recap, we're going to record next week's class tomorrow here at 4 p.m. And you can come here, or you can watch it remotely, or you can then just, at Microsoft, or you can then just, watch it anytime next week. Okay? All right? And in the meantime, have fun with your projects.